KVL is one of the fundamental laws of circuit analysis. It is applied to loops and states that the algebraic sum of the voltages around any closed loop must equal 0. Consider a circuit consisting of a DC voltage source, a resistor R1 with voltage V1, a resistor R2 with voltage V2, and a resistor R3 with voltage V3, where R2 and R3 are connected in parallel. This circuit contains two meshes. Let's first apply KVL to mesh 1. Suppose we start from the battery. In mesh 1, moving clockwise, we first reach the negative terminal of the battery, so we record it as minus V sub DC. Next, we reach resistor R1, across which we must account for V1. Since we encounter its positive polarity first, when moving clockwise, we write plus V1. When we then reach resistor R2 with voltage V2, again moving clockwise, we first encounter the positive terminal of V2. So we write plus V2. Returning to our starting point, the sum equals 0. Rearranging this equation, we have this. This is the result of applying KVL to mesh 1. Now consider the second mesh, the other internal loop. Applying KVL here as well, moving clockwise. When we reach R3, we first encounter its positive polarity, so we write plus V3. Continuing clockwise to R2, we encounter its negative polarity, so we write minus V2. Setting this equal to 0 and rearranging, we have V3 equals to V2. This is actually where the well-known rule for parallel resistors comes from, namely that the voltage across two parallel resistors must be equal. This equality is a direct consequence of applying KVL. We can now continue the analysis. Since R2 is in parallel with R3, we can replace them with a single equivalent resistor R. So R equals to R2 parallel R3, which simplifies the circuit. Note that V2 equals V3, and both are equal to the voltage across this equivalent resistor. We define R as R2 parallel R3. And now we can determine the current I. What is the current R equal to? It is the value of V sub DC divided by the sum of the two resistors, which are now in series, R1 plus R. Once we have calculated this current, we can determine the voltage V1 and V2. Now, to verify KVL experimentally, we build this circuit practically and select a 20-volt battery with R1 equals to 1 kilo, R2 2.2 kilo, and R3 equals to 3.3 kilo. If we now perform the measurements, we can confirm them using the theory developed here. Our V sub this is 20. We calculate the R value. It equals to 1.32 kilo ohm. Substituting in I, we have I equals to 8.62 milliampere. Now we can calculate V1 from this equation equals to 8.62 volt, and V2 also from this equation equals to 11.38 volt. Since V2 is equal to V3, we have. Now we want to measure these values experimentally. It's enough to build the circuit, set the multimeter to voltage measurement mode, and connect it in parallel with each resistor individually. When placed in parallel with resistor 1, we obtain V1. With resistor 2, we obtain V2. With resistor 3, we obtain V3. We consider it a simple circuit to investigate KVL law, consisting of 3 resistors and a DC battery. Okay, the circuit is made up of a node A, where the positive terminal of the DC battery is located here. Resistor R1, which is 1 kilo ohm, is between node A and node B. Also, 2 resistors connected from node B to ground or node G. So here, this column is node A, this column is node B, and this column is node G, or the negative terminal of the DC battery. The ground node is considered. The first resistor is 1 kilo ohm. The resistor R2 is 2.2 kilo ohm, red, red, red. This resistor is orange, orange, red, 3.3 kilo ohms. R1 and R2 are 3. Our DC battery is 20 volts connected between node A and G, positive to node A with red color, negative to node G with black color. Let's first measure the battery to be sure if its exact value. Here I measure between node A and G, meaning the battery value. I'll connect the battery. Yes, the battery voltage. So with DC, or our battery value is 20 volts. Let's move on to measuring V1, the voltage across resistor 1. We can use any of these terminals. As observed, it's 8.56 cross resistor R1. Resistor R2 and 3, according to the arrangement, are in parallel, meaning both have a common upper terminal and a common lower terminal. So R2 and 3 are in parallel. And according to KVL, the voltage should be the same, but we will investigate here. So I'll connect this side to R2. It's 11.44 volts. And for V3, this number should ideally be 11.44 volt. So, as you can see, according to the laws, V2 equals V3, obtained according to KVL. And also the sum of V1 and V2 should be equal to the battery. V1 was 8.56, V2 was 11.44, making a total of 20 volts. That is the battery. Voltage law was well measured in here and verified. As you can see, the agreements between the results are good. There is a slight difference between measurement results with the other results due to the tolerance of the resistors.